All right, so in this video, we are going to be talking about periodic functions, which we've been working with sinusoids, but of course, periodic functions are more general than just that. Okay, so before we get into the definition, let's just draw a random picture here so we can have something to look at and kind of make sense of the definition. So I'm just going to draw, this function here that looks periodic. Obviously, the drawing is not perfect. Actually, just have it repeat 2 times. All right. So let's say this is a periodic function, which we don't know what that means yet, but you might have some idea. Okay, and I usually use these ... dots here to say that I want this function to repeat in either direction forever and ever. Okay, so f of t repeats forever in both directions. Okay, so what does it really mean for f of t to repeat forever? Well, you could think of maybe possibly multiple different ways to describe that, but one that we are going to use is that what does it mean for this function to repeat? Well, all it means is that I can shift the entire function by some amount. Okay, the picture's not perfect, but shift it by some amount so that I actually get back the exact same function. Okay, so if I start with my function here and I shift it to the right, then I get back the exact same function. Okay, if I shift it to the right again, I would get back the exact same function, because remember, I'm saying this repeats forever in both directions. So the picture stops, where I've drawn it, but it would all of these different sections of the function would be lining up perfectly with one another, as long as I shift it by these amounts that I'm kind of demonstrating now. Okay, so that's going to be where the definition of a periodic function comes from. It's going to have to do with shifting by some amount and getting back the exact same function. So f of t is periodic if there exists a number t naught that is not 0, such that if I take my f of t function and shift the entire thing by that amount, then I get back the exact same function I started with. And of course, this has to hold for all t values. That's what it means for those functions to be equal. All right, another part of the definition here. So the period, now we're going to define period of a periodic function, is the smallest such number t naught that is greater than 0. Okay, so the first part of the definition for periodicity, a function's periodic if there exists some amount I can shift by to have my function equal, my shifted function equal the original function. But you can see based on what we did at the beginning that, okay, I could shift by that amount. I could shift by that amount, right? There's actually infinitely many I could even shift in this direction. There's infinitely many amounts I could shift my function by to get back the exact same function. So what is the period of a periodic function? Well, it's just the smallest amount I can shift by and get back the original function. And by convention, we make sure that the period is positive. Okay, you could, define it to be negative, but people just take the period to be positive. All right, one more part of the definition. So the fundamental frequency of a periodic function with period t is, we use the symbol omega sub 0, omega naught, for fundamental frequency, and it's just 2 pi divided by the period t. Okay, and this is in units of radians per time. Okay, that's what this fundamental frequency is. It's like angular frequency radians per time. Okay, so what can we take away from this? Well, I kind of already talked about periodic and period a lot. What about fundamental frequency? Well, this equation is, it should make a lot of sense because let's say I start with my f of t function. What happens if I make my period of it larger? So maybe I take this function up here. Here, I'll even copy it. The wonders of the modern age tablet. And shoot, I thought it was going to, I didn't want it to scale everything. I wanted it to just scale in one direction. I take it back. I'll draw it by hand. Okay, so what happens if I increase the period? Okay, so in other words, I increase the amount I have to shift by in order to obtain my original function again. Well, that would just mean like if I kind of extended my function out, so I kind of spread it out more, right? And then it's repeating, right? So let's say now this is the smallest amount t that I can shift by to get back my original function. You can see that the function's oscillating more slowly. Okay, the frequency, kind of the rate of change, is slower. It's decreased, and that makes sense from this equation because the larger I make t, the more I expand my function out, the smaller this frequency gets. Okay, the more slowly it oscillates. Compare that to what happens when I make my t smaller. In other words, I compress my function, right? Then maybe it looks something like this. Now my function's oscillating much more quickly. The frequency is higher, and this equation says that as well. So if I decrease the period t, then this function is, then the fundamental frequency is going to increase. And you can see that here it's oscillating more quickly. The frequency with which it's oscillating is faster. Okay, so that inverse relationship between frequency and period is going to come up a few more times in this class, so I thought I'd point it out. All right, so now let's look at some examples where we're going to look at some functions and find their periods. And in general, it's actually like not a trivial thing to find the period of a periodic function. It could get very complicated. In this class, we're going to deal mainly with sinusoids or complex exponentials. So the examples today are going to be relatively simple, but it can definitely get complicated. So let's just look at cosine of 3t. Let me draw it for you. So we have our cosine function here. And there can be a few different ways to get the period of functions. Okay, so the first way I'm going to do is let's just go straight from the definition. Okay, so I want some t greater than 0 such that, what does the definition say? When I shift my function by that amount, I get back the original function. And so f of t minus t, and I actually want the smallest. Right, that's what the period was, the smallest such number. I want the smallest t value such that f of t minus big T equals f of t. This side here, what happens when I plug in t minus big T? Well, I plug it in everywhere I see t, and I get cosine of 3t minus big T. And over here, I have just cosine of 3t. Okay. So what has to be the case in order for cosine of some argument to equal cosine of some other argument? Well, I think everyone knows for just the normal cosine function, it's 2 pi periodic. Okay, so it repeats every integer multiple of 2 pi. It's like cosine of x. Okay. So what that means is that if I have cosine of some argument and it's equal to cosine of some other argument, that means those two arguments must be only off from each other by some integer multiple of 2 pi. Okay, if it's true for any t value. In other words, I'm just using the fact that cosine is periodic with period 2 pi, which we know. Okay, so if this is the case, then that means that 3t minus big T is going to equal 3t and then plus some integer multiple of pi. So maybe 2 pi k, where k is an integer. Okay, and you can see over here, I get 3t minus 3 times big T. The 3t's cancel. And that means that negative 3t is going to equal 2 pi times some integer k. Okay, so that means that t is going to equal negative 2 pi k over 3. And again, we want the smallest positive value of t that makes this work. Okay, so we want the smallest positive value. So since we have a negative here, we're going to need this k to be negative. We just want to take it as small as possible. So we'll take k to be negative 1. And that means that our period is 2 pi over 3. Okay, so now we know that this point right here where our cosine function repeats is 2 pi over 3. Okay, but that was a lot of work. We don't want to have to do that all the time. And so we can kind of jump to the conclusion a little quicker. And then after this, we'll even jump even more quickly. So alternatively, okay, I know that cosine of 0 is 1. Okay, and I know that cosine is 2 pi periodic, meaning that the very next time cosine equals 1 is when the argument is 2 pi. Okay, so cosine of 0 is 1, and I'll even write this as cosine of 3 times 0 is 1. Okay, so I really, when I'm trying to find the period, I just want the smallest value I could plug in here for t. The smallest value I could plug in there for t to make this cosine of 3t function equal 1 again, right? That's going to give me this point right here. The smallest value of t I could plug in such that cosine of 3t is 1. So cosine of 3 times 0 is 1. We want the next time that cosine of 3 times something equals 1. So cosine of 3 times t, that's going to give us our period equals 1. Okay, this is the next time after this 0 point when the cosine function equals 1. And we know for cosine of x, that's when the argument is 2 pi. So that means that 3t has to equal 2 pi. That's the first time looking at just cosine, taking this whole argument to be our x. That's the first time that that cosine function equals 1 when that argument's 2 pi. And so you see we get the same thing, t is 2 pi over 3. Okay. And probably you all have seen this before too. But okay, so in any case, let's just look at the fundamental frequency. The fundamental frequency is omega naught, which is 2 pi over t, which is 2 pi divided by 2 pi divided by 3, which is just 3. And so we can see, wait a second, that's that frequency right here, 3. When I have cosine of something times t, that something is the fundamental frequency, right? That's why we keep writing cosine of like omega t, that omega is the frequency of that cosine function. Okay, so that's kind of the fastest way to find the period of this cosine function. Just say, oh, cosine of something times t, well, that something must be the fundamental frequency. And so the period is just 2 pi over the fundamental frequency. So in this case, 2 pi over 3. Okay, so that's kind of the fastest way, but I wanted to show you that you could get it with the definition or with thinking about, cosine in general. So anyway, hopefully that was helpful. Okay, and one other thing I wanted to say, so we definitely call this number the period of this function, but sometimes we also kind of talk about ranges of our function, and we might say that this is like one period. Okay, so we might talk about, one period of the cosine function just being like this part of the graph, right? Something like that. So we use that word period in two different ways, but you can always tell from context what we mean, because if the period is a number, well, it's a number. And if the period is like one period of a function, then it's not really a number anymore. It's like a portion of our function or a subset of the t-axis. Okay, so you can always tell from context, but we do use the word a couple different ways. Okay, let's look at another one. So let's say f of t is 7 times cosine of 3t plus pi over 6. How is this different than the first function we looked at? Well, you can see the amplitude is getting multiplied by 7, and we're adding a phase shift. But if you think about it, the amplitude getting multiplied by 7, that just means my cosine function is, got a larger amplitude, but it shouldn't change anything about the period, right? We're not changing how fast it oscillates or anything like that. So multiplying by a constant out here, the amplitude isn't going to change the period. And also this phase shift is just taking this function up here and shifting it by a little bit. right? So again, it's not affecting the period. It's just taking the whole function and shifting it some constant amount on the t-axis. Okay, so this is the same function as above, just scaled in amplitude and shifted in time. Neither of those operations are going to change the period. Okay, so, or how fast this thing is oscillating the fundamental frequency. So it is the same period and fundamental frequency. Okay, which was 2 pi over 3 and 3. So you could see, I mean, it all works out, right? You would want the frequency to be 3 because it's cosine of 3t, and yeah, it is. All right, so now let's look at the sum of two cosines. So let's say our function now is cosine of 2t plus cosine of 3t. How can we think about this? Well, let's just plot a period of each of them. So let's say this is cosine of 2t. Well, again, we know what the period is of this thing. We just kind of figured it out above for the case of omega naught is 3. Okay, so if this is the fundamental frequency, the period is just 2 pi over that. So 2 pi over 2 gives us pi. And let's also look at cosine of 3t. We just found the period of that was 2 pi over 3, which maybe is like around there. Okay, this is cosine of 3t. All right, so how can we find the period of their sum? Well, if you think about it, f of 0 is 2, right? Because I have a 1 there and a 1 there. And so whatever the period is, whatever the period of this function is, when I plug it in other words, when I look at f of 0 plus t, that better be 2 as well, right? That better be 2 as well. And actually, I'm going to need more room, so I'll move this over. Okay, that's got to be 2 as well. Why? Because let's look back at the definition of periodic function, okay, or the period. It's the smallest such value t naught that makes this true for all t. So all I'm doing is taking t to be 0, right? So I get f of 0 equals f of 0, and then I'll just take this amount we shift by to be negative of the period. So I get f of t. Actually, you know what? Why don't I just look at f of 0 minus t? Yeah, no, I'll look at f of 0 plus t, so we can go in the right direction. But anyway, when I shift by the period, I get back my original function. And I can shift by the period in either direction, even as many times as I want. Here I'm just shifting by the period once. Right? I could do like 0 plus 3t or plus 4t if I wanted. But the definition of periodicity says that when I shift, I get back the original function for all values of t. So here I'm just using the value of t equals 0. So it better be the case that f of the period t equals 2. Okay, and we want t to be the smallest value we can shift by and get back the original function. So what we want to figure out now is when is the first time that both of these functions equal 1 again, because that is the only way that f of any value could equal 2. The only way this number could be 2 is if both of these numbers are 1, because cosine is always between -1 and 1. So the only way the sum of two cosines could equal 1 is if each of them equals 1. So we want to find the first place that both of these cosines equal 1 again. So I'll just plot one more period here. That gets me to 2 pi. And then I can plot 2 more periods here. And that will also get me to 2 pi. So here's 4 pi over 3. Here's 6 pi over 3, or 2 pi. So you can see that this is the first place where these two functions equal 1. So that is the first place where this whole function equals 2. And since cosine, we know both of these cosines are periodic, as I go in the right or left directions, of course, I'm going to get the same thing. Okay, so this shows kind of visually that the period of f of t is 2 pi. Okay, so more generally, most of the time, if you have the sum of two cosines or any two any two sinusoids, the period, if there's a period, if it's a periodic function with a certain period, should be the least common multiple of the periods of the two functions. So you can see the period of the first function was pi, period of the second function is 2 pi over 3, and 2 pi is the least common multiple. It's the smallest number that is an integer multiple of both of these periods. Okay, and that's exactly what we did. We just showed kind of visually here that 2 pi can fit 2 of these top periods into it and 3 of the bottom periods. So it's got to be an integer multiple of both those periods. We want the smallest amount, and that's where the least and least common multiple comes in. Okay, so I encourage you to go on, a plotting website like maybe Desmos or something, play around with some cosines, just take a look at them, see what they look like added up, because I'm not graphing here the sum, just graphing the individual ones. And then you can very easily visually just see often what the period is just by looking at where the function repeats. Okay, we've got a couple more here. So what happens when we square? So what if f of t is sine, let's say, squared of t? Well, let's just plot. First, I'll plot sine. So here's the sine function. It is periodic with period 2 pi. So right there is 2 pi. So what does sine squared of t look like? Well, I'm just going to take all those values and square them. So I'm going to get, whatever I get with these values squared. And then when I square these values, what do I get? Well, that part of the sine function is just the negation of this part. So when I square it, I should get exactly the same thing I got here for all of these values squared, right? Because if I have some number x squared, that equals negative x squared. That value is just the positive version of that value. So when I square all of these and get whatever I get, when I square all of these, I should get the exact same thing. Oops. Okay, and that's true for all of these kind of humps in the sine function. Okay. Where this was 2 pi. And so you can see, what is the period of sine squared of t? Well, look at this, it's actually pi, right? I can shift by pi and get back the exact same function. I don't have to, shifting by 2 pi also gives me the same function, but since pi, shifting by pi gives me the same function, and the period should be the smallest amount I can shift to get the same function, then this shows that the period of sine squared of t is actually pi, not 2 pi. Okay, so the point of this example is to say when you multiply sinusoids, here we did sine squared, you got to be careful. So adding and multiplying sinusoids gives possibly very different results. All right, so last example, I just wanted to look at a couple functions that sometimes students get confused. So e to the j omega t versus e to the omega t. And just so I have something to plot, let's just say omega is positive. So let me plot e to the omega t. What does this look like? Well, this is just a real valued function. And it's just an exponential function. Okay, it's just an increasing exponential function since omega is positive. And it's certainly not periodic. It never repeats, it just keeps getting bigger. What about e to the j omega t? Well, this is now a complex valued function, so I have to plot it on completely different axes. This is the complex plane. And I can't even really plot it properly on just 2D. You kind of have to imagine this sort of animation as t is increasing. And I'll show you what that looks like. So when t is 0, I get e to the j times 0, which is just 1. And as t increases, this angle of this is really just a complex number, right? It's just something on the unit circle. It's got magnitude 1. And this is the angle, omega t. So omega is positive. So as t increases, I just start increasing my angle. I'm just going around and around and around over and over in the complex plane. Okay, that's what that function's doing, e to the j omega t. As t increases, I'm just going around and around and around the complex plane. So I'm at 1 when t is 0, and then I'm just going around and around. Okay, so this function is certainly periodic. Right? It repeats every time I start at 1, and then I'm going to go around the circle, and I'm going to get back to 1. Okay, and we can even find the period. What's the period? Well, we know when t is 0, e to the j0 is 1. So I just want to find the smallest positive value I could plug in for t. Okay, that brings me all the way around the circle and back to 1. So what would that mean? I would want e to the j omega t to equal 1, bring me all the way around the circle. And I want t to be the smallest number that does that. So I just want to go once around the circle. That means this angle should be the entire circle's worth of radians, just 2 pi. So omega t should equal 2 pi. And so t is going to equal, the period is going to equal 2 pi over omega. Okay, so if you gave me e to the j for t, what's the period of that? It's just 2 pi over 4, which is pi over 2. Okay, so you can easily calculate the period of different complex exponential functions because you can see that that is going to be your fundamental frequency, just like for cosine and sine. And then you can easily calculate the period just doing 2 pi over that. Okay. Okay, so these complex exponential functions are going to play a huge role in this class going forward. We're going to be using them all the time. So I just want to make sure we're on the same page about exactly what's happening. All right, so that's it for this video. I will see you in the next one.